Hello everyone. Today is the 17th day of Leetcode 75 challenge. Let's begin with the 17th question. Question 208. Implement try. Prefix tree. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. You are required to design a data structure called try or prefix tree. Okay? And this data structure should allow storing and retrieving strings efficiently. Okay? So, but what is try, right? So, if you look at here, a trie, pronounced as try, a prefix tree is a tree data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications of this data structure, such as autocomplete, spell checker, and dynamic searching. Okay, and question related to the dynamic searching we will be doing in our next problem. So this is a try. Try basically works on efficiently on storing and retrieving anything related to strings. Okay, particularly strings only. So it is which it makes the time complexity much more efficient and much more less. Okay, so in this particular problem you have to do the same. You need to implement the following operations: inserting a word, insert the given word into the try; searching a word or search a word, return true if the given word exists in the try, basically was inserted before, otherwise we return the false. Starts with prefix, returns true if there exists any word in the try that starts the given prefix, otherwise return false. I hope you understood what is prefix, but what is this basically means is that suppose in the try you have a word apple with you. Okay, and I gave you a prefix, suppose app. Okay, so when you will traverse the try, you can see that we have a word with prefix app. Okay, suppose let's take another example to understand this. Suppose you had HAPPLE, right? This won't be happening because the prefix is not APP, it's HA, right? It starts with H, not A, right? That's why it won't be considered. So this is what they're trying to say. If anything, if there is a word exists with this particular prefix, please return true, otherwise return false. Okay, coming to the constraints of the problem, the word length and the prefix length which will be given to us will be from 1 to 2000. Word and prefix consist only of lowercase English letter, no capital letters will be there. At most, 3 into 10 to the power 4 calls in total will be made to insert, search, and starts with. Okay, so I hope you understood the problem explanation. Now let's move to the next slide. Now let's understand the input output explanation. So if I take this example, so first try. So first we call try. So this basically creates a data structure, nothing else. Okay, suppose this created a data structure. Now the second operation is insert. So in insert we have the word apple, right? So we will insert apple to within this try. Okay, take this as a try. Okay, this is a try. Now again there is a search for apple, right? If you go in the try, we have the apple, so we will return true. And for this we return null because we are not, of course, we are not returning anything. We are inserting, right? That's why it's a null. After that, there is another word search, another operation search with the word app. So that's a complete word, right? It's not a prefix. Please keep that in mind. It's a complete word. So in the try, we don't have any word app or app, right? That is why we return false for it. Okay. After that, we have this operation starts with. Now, in starts with, we have app. Okay. And in the try, we have the word apple, right? And in apple word, we have the prefix as app in it, right? That is why it's true. Now there is another insert of app. Okay. So we will add app to our try, and it's null because there is nothing to be given as output. After that, there is a search operation, and that is for app. Okay. So yeah, it's search. So we have to basically search this complete word in the try. So apple does not belongs to app, but yeah, we have the app in itself in the try, so it will return true at the end. Okay. So this is how the operation should be working in a try. So I hope you understood the input output explanation. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Let's start it by understanding the goal first. We are asked to design a data structure called a trie, prefix tree. And this data structure allows efficient storage and retrieval of strings, especially useful for problems like autocomplete, spell checking, searching of words, inserting of words, and finding for the prefix of the word, also dynamic searching. So the trie must support these three operations, which are insert, search, and starts with, which I already explained you earlier. Now, instead of going with a brute force solution, like we will store every word, like we have apple, right? So suppose let's take dictionary. Suppose in dictionary we stored apple. Just I'm taking an example, okay? So if I'm asked to search for app, what I will do, or not, let's not take dictionary, let's take a list itself, okay? A dictionary will be much more easier, because in dictionary what you can do is that in brute force you can directly first go and ask for that. If I'm asked to search for a word, so I can directly go and take it in O of one operation, right? But if I'm not getting it, right, then it will be false. Second, you can take this as a prefix, right? But for prefix, you have to iterate the complete dictionary. Okay, it will take another time complexity, because what you will do, you will take each word, iterate it. You will take each word, you will iterate it. So it will be like, let L be the average size of the words into the total number of words, right? So L into N will be the time complexity for that, and it will be a lot. Since our condition was given as, if I remember, it was 10 to the power 4, so it will be a lot, right? So to get rid of those things, or to make the time complexity much more efficient, what we could do, we could use try, because it is a completely string operation, and this is what a try helps us to do, right? So that is what I've written here. Instead, a try organizes words character by character in a tree like structure, which makes prefix based operation very fast. Okay, let's understand what it means by tree like structure. Now let's visualize the process. A try is a tree where each node represents a single character. A path from the root to mark end node represents a complete word. So what does that mean? Suppose if you are starting with a root in a tree, okay, and I have given you a word, cap. Let's take cap first. So what will happen? We'll come here. You will store C here. Then you will come in A. You will create another. Then you will come in P. Then you will create another. Okay. So this says that from C you can go to A. From A you can go to P. Okay. So then you have cat. Okay. So in the tree we already had C with us. Then we had A with us already, right? But we don't have T, right? So what will happen? A new T will be created. You can see how the space is reducing here. Then the dog, right? Since we don't have D initially from the root, so what will happen? A new kind of what you could say path will be created. Okay, so this will be the try. So whenever a person comes and says I want CA as a prefix to be searched, so what will happen? It will come to the root. It will see, okay, we have C, okay, we have A, right? So we have CA as a prefix. Then if a person comes and says I need a cat word, right? Or you could say cat word, right? So what will happen? We have C, we have A, we have T, cat. Okay, but if a person comes and says that, okay, I want to insert a word, CATY. What will happen? We don't have to create a new, that one space. Rather, since we have C, we have A, we have T, just we will increase it with Y. Okay. So this is how a try grows, and this is how a searching is done in a try in a higher level. Okay. So I hope you understood this visualization process. Now let's move to the next slide. Now, how we can simulate this? So before going and understanding this part, I will give you the complete idea of how a try is created from scratch. Okay. So I have taken this example here. Okay, and this is the class try class which I have created, and each try class, or each try will have a array or list of 26 size, and a word is word end. It is a boolean, true or false. Okay, so whenever this class will be created, a data structure will be created like this. Okay, here what will be happening? We will be having is word end. I will be writing it as we. Okay, we initially as false. Okay, and there will be this 26 size array having all the space for storing the characters. Great. Right now it is false. Okay, instead of writing we as false, what I will be doing, to make it much more cleaner, I will just write f. Okay, that's all. Just keep that in mind. This means we. So what will happen? We will start with this word. Okay, ball, and we will go with the insert operation first. Fine. So we start with the root, and we see that, okay, so we will create a try. Fine. As soon as we create a try, we see that we don't have B in our try node. We will add B. Fine. After that, as soon as we create this, a new reference node will be created this way. Okay. and this reference node will be pointing from the B. Okay, this is a reference node to B. Fine. And here what we will do, this will also become false. Fine. Then after that, from B we will go to A, and we will come to this reference node now. And here we see that we don't have any A, right? So what we will do, we will add A here, and a new reference node will be created from A this way. Okay, with false. I will tell you why we are writing false, but let me draw the tree how it's going to work. I hope you have got till now what we are trying to do. We started with a root node. So suppose it is somewhere here, okay? And since from root node we have to do something, right? So we created a node, try node, which stored this B and created a new reference node, try, pointing from the B. Okay, we will get it how it's working, right? Now L. From A we created a new reference node, right? And we are standing here. And since we don't have L here, what we will do? We will add L, and a new reference node will be created from here, from L. It's reference node to L. Okay, and this will also become remain false. Now from this L to we came to the last L, right? And similarly, same situation, we don't have anything, so we will add L here, and a new reference node will be created from here. Okay, and this will be false. Now, if you can see, the word is completed, right? The scanning of the word is done. Now what will happen? This false, which we wrote here earlier, this will be from false. It will be swiped to true. Okay. Now why true? This true will basically depicts that this is the end of the word. Is end of word. Okay. This will depict, hey man, we have completed our whole structure of iterating the uh, one single word, and we have created one of the branch for it, and this is the end. Fine. Okay. Now going back. Now we will start with this word. Okay. Bat. Okay. Bat. Now we can see that we already have B with us, right? We started from the root node again, right? Because it's a new iteration. But we came here, we saw, okay, we already have B with us, right? And from B, B is pointing to A here. So we came here and we stand here. Now we will iterate to A. Okay, so A. So we are already standing at a reference node from B, which is already having A. So what will happen, since we already have A, so it will come to back in this particular reference node. Now when we come here, we see that it's T, right? And in the reference node in which we are standing, or the try node, we don't have T in it. What will happen? We'll add T to it, right? And as soon as we add T to it, a new reference will be created from that T. Okay, like this, and it will be false. Now we are standing here. Now after T, the iteration is complete, right? So what will happen? If you remember, this false will be turned to true, saying that, hey man, if you start with B, then if you go for A, it's fine. If you go for T, after that, from A, if you go for T, not L, that is, and then when you go for, that's the end of the particular word after T. If you go for bat, but if you go for ball, then it won't be standing at T, because from A you will be searching for L in this particular reference node, right, rather than T. Then from if you get the L, then L is pointing to this reference node which is also having L, right, rather than pointing this one. Okay, so I hope you're getting this, how the references are working and how the nodes are created each time this particular try node is created. Okay, great. Now let's go and iterate this particular word bag. Again, the same scenario. You start with the root node. Since we're doing the insert operation, we see that we have B, right? And B is pointing to A reference. So we are standing here. Great. Now A is pointing to this particular reference class, you could say, or you can say reference node. But here we see we have L, right? We have T, but we don't have G because it's G, right, in the bag. So as if we have understood till now, we will add G here. Let me write it again. We added G here, and what will happen? A new reference node will be created with the G, right? Sorry for my diagram here, but yeah, a new reference node is created here with false, right? And we are standing here now. Now this is that, okay, this iteration is complete now, right? We can see the iteration is complete. So what will happen again? This F will be converted to, or this false will be converted to true, right? Great. We're done with that. Now we came with the cap word now. Now we started the root node and we saw here in the reference here that we don't have C with us, right? Which is the starting character for the cap. So what we do, we add C here. As soon as we add C here, a new reference is created from the C. Okay, and it is marked as false. Then from C you come to A, Then since we are standing here, we don't have a here, right? So what we will do, we will add a here, and another reference node will be created from a, and this will be also marked as false. Okay, now we are standing here. Now we come to p. Now since we are standing here, we don't see any p here. What we will do, we will add p. A new reference node will be created from here for the p. Okay, and this will be marked as false, and we are standing here now. Now since when we are standing here, we can see that okay, the word is completed, right? So what will happen, this false will be converted to true, depicting it is an end of the word, right? Simple as that. Now this iteration is complete. Now we start with the car. Again we go back, we see that okay, we have c in the reference node. If we check from the root node, okay, then we come and stand at a. Okay, we're standing at a then. Okay, so we also have a to with us, right? So a is pointing to this p, right? So we come to this reference node now. But since after a we have r, right, and here we don't have any r, so what we will do, we will, as soon as we will add r here, again a new reference node will be created, a class node, try node will be created with false, and we will stand here. Again the same scenario, since this is a complete iteration is done, right? So this false will be converted to true now. Then and the word is completed. So if you can see, we have completed our all the iterations by adding all the words in it, and if you can see, it has created a tree like structure, right? Now after having doing all this, our next operation is what, searching. Okay, now for searching, let's me write it here, search, and we will search for, suppose let's search for ball first. Okay, then we gonna search for bal, and let's also go for ca, t. Fine, start. So if I searching, right, so what will happen, we will come to the try, we will, from the root we will ask whether do we have b with us on the first reference node. It will say yes, we have it here. Okay, so as soon as we have it here, this b is pointing to this reference node, right? So we will come directly to this reference node here, and we will stand at a. Okay, now we will ask, do we have a in that particular node? It will say yes, we have it. So what will happen again, after having it, we will directly jump to its next reference node here. Okay, and here it's only l, not t nor g. Okay, now do we have l with us? It will say yes, we have l here. So from here l, we'll directly jump into this particular reference node, and again we'll check whether do we have l. It will say yes. So as soon as it says yes, we'll again jump to this particular last reference node, and we'll stand here. And after that, when the iteration is complete of this complete word, we will ask in if in the last node is word, is end of word is true or it is false. If it is says it's true, that means we have completed our search and we have got the word we were searching for. But if it is false, that means that we have not completed, we didn't got the complete word. Basically, this iteration is not completed till now, the tree iteration. Okay, so since it is true, we have got the words true. Okay, fine. Let's start with this another character, bal. Okay, again the same scenario. Please keep that in mind. Again, root will ask, do we have b? We have b. Again, we will stand at a. Again, a is matching, so we'll go and stand with l. So l is matching, right? So we're standing itself. Then we will come to this part, right? Now this word iteration is complete, right? Then we'll ask, is the end of word true or false? It is false, right? Since it is false, that means that we don't have a complete word as bal in our complete try. As you can see, we already don't have. We have ball, we have bat, we have bag, right? We don't have bal, so it will return false. Now coming to the cat, the above root node will ask, do we have c in our first reference node? It will say yes, we have it. So from here we have it, so we will jump to this particular reference node. We'll stand here at a. Now it says that do we have a? Yeah, we have a, right? So what will happen, from here we'll directly jump to this particular reference node, and we will search for t here. But we don't have t. What we have? We have p with us, right? Not an r, not t or anything else. So since we don't have this, we will directly return false, because first scenario is that you have completed the iteration of the given word, and at the end you will check whether the is and word is true or false. If it is true, that means we got the word. False means we don't have the complete word. Otherwise, in between, Even the word search is not complete, like you can see the example of cat here, we will return false because the last character is not matching in the pointing reference node. Okay, so this is how the searching will be done. Now let's look at starts with. Okay, for starts with, let's take ba as the prefix. Let's take ct as the prefix. Let's take b. I think two examples are enough. Let's take another. Let's take BAL. Okay, L. Okay, let's take this. So since we have to look for a word which starts with a particular character, right? If you go for BA, root will check whether we have B. Yeah, we have the B. Same scenario. As soon as we figure out we have the B, we will directly jump into the next reference node. And here from here we will check. Do we have A? Yeah, we have A. Right? From here directly we will jump to the next reference node. Now, word search is complete, right? Nothing to be worried about. If we have got this word, we will directly return true after the iteration is complete for for this word. Okay, no checking is required. Now we will see for the false case for the ct example. Okay, again the same scenario, root will check, do we have c? Yeah, we have c, so directly we'll jump into this reference node. Now from here we will check, do we have t with us? No, we don't have t, right? As soon as we don't have a particular character and the iteration is not completed, right, we will directly return false. We won't be checking whether it is the end of the word or whether it is not the end of the word, because that does not matter, because you're looking for a prefix in a given complete word. But here we can see we don't have t itself, right? So then only we will return false. Now let's take the example of ball here. It's a complete word, right? It's not a prefix, but let's see what happens. B, then we'll come to A. Same routes, same rules. From L, then again L. As soon as we stand at L, we will standing at this particular node, right? As soon as this iteration is complete, we'll just return true because we have got the complete prefix, right? It does not matter whether that prefix is a word or a part of a word. Okay. So this is how a starts with function will be working. So I hope you got the complete idea from scratch to the starts with and inserting along with the search operations, how it's going to work and how the tree is created, and what are the important parameters such as creating a list, creating a bool for storing true and false, and what is the meaning of this, right? So let's move to the next slide. Okay, so if you can see how we can simulate this, which we already did, we will create a node here, children node 26, right? And children will be having 26 length and is word and will be false. This is a boolean, right? Then we will be having the insert operations. We start with the root. If it is missing, we move forward by adding it in the list, and we move forward, if you remember, right? And search operation is there. We check for the word. If it is missing, we return false. Otherwise, we return is end. From the is end function, we try to return whether it is true or false of the end word, and starts with operation. So this all the functions which I've written here contains key, is end. This will be explained in the approach part. Okay. So I hope you understood this. Now, what we figured out from the problem? We figured out that by storing the word in a tree-like structure, we avoid repeatedly comparing full strings. Shared prefixes are stored only once, making the structure more efficient for large word sets. So if you remember shared prefixes, that means that if you have a word apple with you and apps with you, okay, what will happen is that you will store a, p, p, l, a, right? Then for a, you won't be storing again one more a, right? If you remember what you used to do, it's the same prefix, right? It's common one. So yeah, a, p, p. Then from here we can create another word as s, right? This is what this 4.2 point describes. Searching or inserting a word of length l takes O of l time, right? Makes sense because searching for a word will take the time complexity of the word length, which is optional compared to checking against all the words. How? If you remember previously, what we were doing, if in the dictionary case, if we have multiple words, right, and if we have to search for a particular word, right, either in the dictionary you can directly get the word in O of one operation, but in the prefix scenario, what will happen? You have to search or iterate the complete words. This design ensures that insert, search, and starts with are efficient and scalable for multiple queries. Okay, so I hope you got the complete intuition format from scratch to the ending part, and also about the points what you figured out. So let's move to the next slide now. Now, since we got the intuition of the problem, let's look into the approach how we're gonna solve it. Let's start by defining the node class, the most important class you could say. We create a node class to represent each character node. Node class means try node, you could say, the one which was creating each time, right? And how it is, we'll create a children of size 26 array to hold the references of A to Z. If you remember, in each time when we were creating a reference, if suppose it was cat cat, if it was cat cap, it was cat ca, any other word, let's cad, let it be. So what was happening, it was storing, and since t was here initially, then since t was not there, p was added, then d was added. There could be a case that you might have 20 all the 26 characters, right, to be stored in particular reference. So that is why we have a size of 26. Is word end, if you remember clearly, we used to check, it is a check mark for finding out whether the word has been completed or not at the end. These are the two main components of a try node which we were considering. After that, provide helper functions. These are the helper functions within the node class, right? Other than that, first is the contains key. This helps in checking if node has a link for the character or not, or ch. Suppose if you are inserting something, right, and if you are looking for a, do we have a? No, we don't have. So what will happen? We will add it, right? So it is basically doing what? ORDCH. Suppose a. What is the ASCII value of small a? It's 97 if I'm not wrong. And suppose you got uh, another word as C. Let's take C. So it will be 97, 98, 99. Okay. Now you have been said C here. Okay. So ORDCH means 99. It basically takes the ASCII value of that. Okay. 99 minus ORD of A, which is 97, gives me 2, right? So in the list children 0, 1, 2, 3, 4. So here A was stored, B was stored, then C will be stored here. Getting my point? This is what is actually happening here to make it much more easier. Or directly look for, if you also want to look for a character whether we have E or F with us, so what we will do, we'll just subtract the numbers and we will directly go to that index and we'll look at it whether do we have or not. Like here what we did with 2, in 2 we will go and see whether we have C. If we don't have C, then what will happen, we will add. If it's an insert operation, we will add it there. Okay. And how the add function works, similarly we have the character, we go to that index and we add that node to it, right? Adding node means, let me make that clear to you. Suppose this is the empty class, empty reference node of try node, and it is false. Okay. So what will happen, first we will check for contains, right? In this, suppose we don't have it, suppose we have A and B, we don't have C, right? So what will happen, in this part in C, we will put the reference of this node, a new node will be created, if you remember, right? And we will be having the reference to this node. Actually we are not storing A or B there, we are just storing the references for that nodes, right? This is how it's working. I hope you're getting this. Now get ch is also the same thing. We will just put the character in which node we are standing at and we'll get the values. Set end is a function which marks the node as the end of the word, is word end as true. So when the word iteration is complete and suppose you're standing at this particular node which has been already created, and that will just mark as true. I hope you're getting these points, right? Because you already did the iteration and this is the meaning of the functions which you are creating here. Is end. This basically check if this node is the end of the word or not. That's all. I don't think it was such more complicated to understand. I hope you got it. Okay. Now at step 2, we define the try class. Okay. This is a try class, which is the main class. First we created the node class. Now we will be having the class try to run the program. We initialize the root node. Why? The root node serves as the starting point of all the operations. It's like this. Suppose we created the class try node earlier. Okay. Suppose this is done. Now this is the main class try, which will be calling all the previous functions which we declared here, which will basically declared here, and we will called here. And the root, or the starting root node, if you can see, try node is created here, right? Self dot root try node. So somewhere we have to start, right? So this is the starting point. Now step 3 is the insert operation. We will start with the root node, as we seen earlier. For each character in the word, if the node does not contain the character, create a new node. What function it will use? Contains key. If you can see here, it's a contains key, right? So if you can clearly observe the code here, we are iterating, suppose a character ball, right? B, we're at B, suppose. Then if not, we will call this function by passing B. What will happen? B minus A will happen, right? If you remember clearly, it's 98 minus 97 gives me 1. So in that particular node, we will go to this 0th index in the list, okay, in the list of that particular node. We will say if it is there or not. We will say we don't have anything to it, right? So what will happen? We will put it. We'll pass this character. We will put here the try node in this index, the reference, and a new node will be created here for this particular character. Look, we have passed the node here. And if we have it, suppose if we have it, what will happen? Current node. Suppose if we have it this way, A B, and we are writing A and B for our better understanding, and B is pointing to this, right? And we are standing at B. Suppose we have it, right? So what will happen? We will get B. Uh, it was 98 minus 97, right? Get function, if you remember clearly, this is the get function where it is this one. Same thing we are doing, right? So we will get one, right? In the one index, we'll try to find in what is the reference to it. This one is the reference, right? So we will get this reference stored in this current node, and so we will be standing here again the same way, right? So that we can move ahead. And after all of this is done, we will be standing at the last node. Logically makes sense. In that, what we will do? Current node, set the end function to true. Look, the set end, this is already marked as true here, right? And initially everything will be false. So I hope you understood the insert operation. Now let's look for the search operation. Same as that one. We will iterating the complete, suppose ball we have taken. We are standing at B. And if current node contains the key, suppose if we have B here, it does not contain, sorry. If it does not contain, if it is false, we will return false, right? Suppose you don't have the reference here, we will return false. But if we have the reference and we are looking for this ball word, we will go to its next reference using the function get. I hope now you're getting it, right? We will use the get function. Now, when this complete iteration is done of ball, we will be standing at per particular node, right? It could be the last node also, or it could be the middle node also. But if it is a middle node, it will be false, right? Because there would be much more references down. But if it is not the middle node, it will be true because this will be the last reference. So that is what will be written from here. Now, step 5 starts with the operation. It is also same as the search operation. Just you could see, we are not writing or calling the is end function here. We are just returning true. Because look, if we have completed the iteration, suppose it was BA, right? Then it does not matter what is the word leftover word after that, because we have already did it, right? That's all what matters. But in BA, you didn't got A, right? In the middle of the iteration, we will return false. So this is what all the steps about. So I hope you understood the approach explanation. Now let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. Now here you could see try node is there and the try is there. Okay. Here we have created this children's. This is a list for each of the node, and this is the word and true or false. This is the function keys contains key to check for the whether it is there or not. To add the node character, to get the character's reference, to set true or false, or checking whether the word is the last or not using the isAnd function. So I hope you understood this now, right? Very much clearly. But you could just look over the code to understand it. Now this is the main function. Okay. Here also, if you can see, it's pretty simple. We just have to create and initialize the first node, right? And after that, what we do, we just go for it. We're inserting the nodes. This is the operation. When we search the node, this is the operation, and this is the definition of starting the word. Okay, starts with prefix. So now let's understand the time and space complexity here. The time complexity is L plus P. What does the L represents? L represents the length of the input word or the prefix word. Okay, and N represents the number of word inserted. Okay, so if you remember what we were doing, if apple was there, suppose app, not apple, again and again. Let's take it apple only. Yeah. So this took L time complexity, right? But again, you have apps. What's happening? You're just iterating this word only, right? You're not adding it in till here. But after that, you just added s. That's why it's L plus P. To make it much more clear, much more understanding, in insert operation, you traverse each character of the word once, correct? Each operation is O of 1 since you are indexed directly into the array or dictionary. That is why time complexity for that insertion is O of L. Now searching the word is the same logic. You traverse the word character by character. That is why it takes another O of L operation. Okay. The starts with is the same traversal as search, but only up to a prefix length, right? That is why its time complexity is O of P. Okay. That is why the total time complexity comes out to be L plus P. Now, why the space complexity is N cross N L. N is the number of words. L is the average length of the each word. Okay. Now, in worst scenario, no shared prefixes is there between the words. Then and only N cross L time complexity might be there. Okay. Space complexity might be there. My bad. Because suppose no shared prefix means I gave you apple, I gave you cat, I gave you ball, right? It will all take, different spaces. That's why it will take L length of this each characters into N, right? So basically 3 into 3. I hope you got the space and time complexity definitions. Now let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. So I have also brought on a code here for a better understanding. Okay. So I will not give the complete dry run of the particular you know, problem because it will take a lot of time. But I will give you all the complete gist of it. Okay, let's start. Suppose it's try. Try is called. So a new data structure is created. Then there itself is the insert operation. Okay, and since we get the insert operation, let's come here and look for the insert operation. It is right here. The current node is the self root. So we're standing here then. Then we iterate the word. What is the word? Apple. Let me write it here. Apple. Yeah. So if not current node contains the key, so we'll pass this A, okay, and we will look for the contains key. Return this. So in our list, okay, we are passing 97 minus 97 gives me 0. So in 0th index in the list, do we have A? No, we don't have anything, right? So it will return true. We don't have it. So we will call the add function and we'll pass the A again here. So in that position, so in this position, a reference is created with a new node. Okay, false. Got it. And after that, we call the current node dot get this character again this character, right? And in get function again it will be 0, right? So we go to the 0 and we call the reference. So we come and stand here, right? This is what insert function is happening here. Now again it's A is done, right? Then we will have P. Again same scenario. We will check. We will store P. Again a new reference will be created like this. Okay, with false. And we will stand here. So I'm hoping you got this point, right? If I keep on doing this, it will be a very long video. Okay. Let me just make it a shortcut here. Then there is L, right? L, then with F, right? Then again there is E. Okay, fine. Now let's look for the search operation. Word apple is there. So we come here. Again, the same scenario you could see. We are starting with this root node. We're starting with this for the search. Okay. Then again the character, we're standing at A. If not contains A, if we come back to this contains, we have the A, right? Because if we subtract 97 with 97, we get 0. So it's false. So nothing is done. So we go to the next, calling the get function. So we go, it's 0, right? So we're standing here. Now you could see it's P, right? So I don't know the ASCII value of P. Let me check once. So it's 112, right? So ASCII value of P is 112. So what will happen? 112 minus 97. Okay. So what will give? 15th. So okay, current node get. So character is there in the get function 15. So in this reference node, in the 15th index, we'll check, do we have P? Yeah, we have the P, right? So please call its reference and come and stand here. Okay, we're standing here now. So it will keep on going like this. And at the end, we will be standing at E's reference. So is the current node is end, right? This is the last reference node if you remember for E. Okay. So yeah, we will return this. And since it is true, it will be returned true. And that's why we got true here. Okay. So similarly, it will happen. And let's go with the starts with APP. Okay. So again, the same scenario. If you see here, we have the root, we have the A. Again, we check, do we have A in it? Yeah, we have it, A. So don't return false. Please go and to the next node, P. Again, please check if it is null or not. It is not null. So again, go to the P's reference and stand here. Okay. So again, come here. So now iteration is done, right? And we are standing at this node. So we'll just return true because we got the complete word or the complete prefix. So I know the try run was pretty short and pretty quick, but this is the same thing what we did in the earlier part and we understood in the approach part. So I'm keeping this on you to do the dry run. So if you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, and the code. And after that, do a dry run by yourself on 2, 3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. So now let's move to the next slide. Now, since you are familiar with the problem and the solution, let's move to the lead code and code the solution. Let's start by defining the class try node. Okay, definition of init constructor self. What we will have? We will have children equals to none into 26. Now, if you are wondering why I have kept this word as children, because suppose if you are standing at A, right, and you need the reference for B, P P L E, like apple, right? So P is a kind of a children to A, right? That is what it means. Self dot is word and will be false in default. Now then we will have a function def contains key, okay, and we will have self in it, and I guess we will have the character with us, correct? We will return self dot children order of the character minus ord a is not none. Okay, now let me copy this because it will be used again and again if I'm not wrong. Okay, so definition of put function, it will have self with it and the character with it, and what we will do, we'll just put it here. In this part we will add the, since it's put, right, so we'll be having node with us, so here I will just add the node also, right? Now definition of get is self and the character, right? And we'll just do this. Okay, after the get we have set end, and we'll have self with us, and it's nothing, just this. I will take this and add it here, and I will make it true. That's all, right? Okay, then there is definition is and self, and that will be self dot, or let me just write it here directly, right? That's all, right? Okay, now let's fill up this. Self dot root will be new try node, right? Then after that, let's code the insert function. Current node. Okay, current node will point to this root node, or self dot root, I guess. Self dot root. Okay, and the for, we will iterate for character in word. If not in current node dot contains key function, right? We pass this character. If we don't have it, right? If we don't have it, then we will return false. Sorry, since it is an insert function, right? So if we don't have it, we'll just add it. That's all. Current node will have, we'll call this put function thus, and input what we pass the character, and we pass the try node. Okay. After that, current node equals to current node. We will get the next reference to it by passing this character. Okay, and at the end, it will be set end function. Okay, so this, I hope you understood this. This set end will make it mark it test true because the word is completed, right? Now we'll copy this whole scenario, whole code here, and put it here. Now since we are searching for a word, right? So if it is not present, we'll just return false, right? And we'll go to the next character, and at the end it will be just is end. So this is end will return whatever the value of is word is there, so that we can know whether it is true or false. Okay. Okay, again, starts with is also the same thing. Here also we'll just um, return false, and here it will be written true. Okay, so let's try submitting this problem for the sample test cases first. So it will be prefix. It's my mistake here. So let's try submitting for the sample test cases. Now let's finally submit our solution. So we have successfully submitted our solution. Now code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.